Okay. So there were few things we talked about in the last lecture, right? So one was, so let's see. So we talked about homomorphism and inverse homomorphism, and we showed closure under homomorphism and inverse homomorphism for regular languages, right? And then, if you recall, we also said uh, something like, so we also said something like, so if you have, for example, L and H inverse of H of L, right? So let's see where it is. Okay, it's here, right? So we talked about a homomorphism H, and then we also talked about H inverse of H of L. It's a superset of L, and we gave an example here, right? We gave an example, and then we said also that if you consider H of H inverse of L, it can be a subset of L, right? And then, so can you give me an example where it's a proper subset? Sorry. So what is your sigma, what is your gamma, and what is the H that you are? Yeah. So can you give me a concrete example? So we are trying to show this. No, this we showed. We are trying to. Yeah, tell me. And H, how is H? H is from sigma star to gamma star, right? So what is your L? L is 0, 1, 2. 0, 1. L is 0, 1, like this. So is it gamma or is it L? So is it gamma? You are saying 0, 1, 2. Okay, so this is gamma and this is also equal to L. Okay, and then sigma is 0 and 1. Okay. I mean, you can also have AB maybe. Okay. Then H of A is 0. H of B is 1. Yeah, right. Right. So we defined H inverse of L. So let's bring this here. So H inverse of L is this thing, such that Hx belongs to L, right? So now what is the H inverse of L? So Hx belongs to L. So these are your A and B, correct, in this particular set, right? And now H of this set, AB, what do you get? you get 0 and 1, right? So you see that age of 8 inverse n can be a strict subset of it. So we discussed this. So, okay. And did you try this to show for, so we were proving, in fact, that regular expressions, right? I mean, regular languages are closed under homomorphism, right? And we're trying to prove this using the regular expressions, right? So what did we do? We started with, so essentially we had a set A. So we wanted to say that HA is also regular, correct? So this is what we wanted to prove. And so for this, we had R, and we started with H of R, right? And let's say we called it R prime. And and of course, so L of R prime is regular, right? So this was the general proof idea that we were looking at in the last lecture. So L of R prime is regular. So essentially what we wanted to show is that H of A is the same as L of R prime, right? If that is the case, then you in fact show that H of A is regular. That was the idea, correct? So we were trying to show that regular languages are closed under homomorphism. So you consider a homomorphism H. Now, one way to do this is to consider the regular expression from A to R. You consider H of R, which is say R prime, and then you show, and of course, since it's a regular expression, we know that L of R prime is regular, and hence, if we can show that H of A is nothing but L of R prime, then we also show that H of A is regular. Clear? This was the proof idea. And we started with the base cases, correct? We started with what were the base cases? R equal to A, epsilon, and can be the empty set. We showed it for this. Then we showed for R equal to R1 plus R2. We showed for R equal to R1 dot R2. And then we said, what if R equal to R1 star, right? So, okay. So now, and then what we wanted to say is that L of R prime, right, which is L of R1 star prime, correct? This is same as the H of L of R, right? So this is what we wanted to show, right? You had the regular set A, and R is the regular expression for this A, and we wanted it to do it for R star. So we did already the last lecture for this one and this one, right? And this is something, and it's exactly the same process. Okay, the only thing is that what we said is that when you are using R star, we should use the fact that R star is the same as this thing, right? For example, so the language corresponding to R star, is the same as the union of all these languages, right? So this is what. So what we are saying, the language corresponding to R star, it's a union of n greater than equal to 0, L of R of n, right? So this you have to use somewhere, right? This is the only tricky part, and you should try to work it out yourself. Okay, right? Okay, so this completes the proof, and then we talked about inverse homomorphism. And how do you show closure under inverse homomorphism? We talked about a DFA, right? So if you have a DFA, let's say you have a DFA for the language, so you have the homomorphism H from sigma star to gamma star, right? And you have something like this, a language L, and you can talk about, and we are saying, suppose this is regular, right? And what we want to prove is that H inverse of L is also regular. This is what we want to prove, correct? And what did we do? Since this is regular, since it is given that this is regular, we could construct a DFA A, right? We could construct a DFA A accepting L. This we can do. And now we also construct A prime with the same state space, right? So it will also have, suppose it has the state space Q, this has the state space Q prime, then we are saying Q prime equals Q, the same state space, correct? And then suppose if you have, let's say, you just consider all these things, right? So you just consider, so if in general, the homomorphism gives you something like of this form, but you can restrict your attention to sigma to gamma star, correct? And how you are going to simulate a transition in A prime? How are you going to simulate a transition in A prime? So you look at, for example, if you have in A prime, right? If you have Q1, so this is in A prime, right? So suppose A prime, so let's define this. Okay, let me try to put things a bit. Right? So if you have, for example, A prime was Q prime sigma delta prime Q0 prime F prime, then we said you have to define the delta prime, right? So delta prime, how are you going to define it? So suppose delta prime of QA Q prime, correct, should be delta star. What is delta? A equal to Q gamma delta Q0 F, right? And we have already said that here this Q prime is the same as Q. What about the F prime? Okay, so we'll come to that maybe later. But and what about the Q0 prime? It's the same as Q0, correct? And then we are talking about this delta prime of QA Q prime equal to delta star Q HA Q prime. Okay, so there exists Q prime such that Q on HA goes to Q prime. If this is the case, then you have delta prime QA Q prime, right? Okay. Next, what is the F prime? F prime equal to F. Okay, good. And then you have to prove. So this is just you are giving the construction. And now you have to prove that indeed this is the case that LA prime equal to LA prime equal to H inverse of L of A, right? So once you have the construction, you need to prove this, correct? And you can, how are you going to prove this? In two ways. L of A prime is a subset of H inverse of L of A, and then L of A prime, it includes H inverse of L of A, right? So you have to prove this. So essentially, how are you going to prove, let's say the first one here, how are you going to prove this thing? That L of A prime is a subset of H inverse of L of A. So you start with some X. Okay, you start with some X. Let's say X belongs to L of A prime. And then you need to show that indeed X also belongs to this, and vice versa. And you can prove this maybe using induction on X, on the length of X. This is one way to prove this. Clear? but you have to do these things yourself. Otherwise, if I mean, like if there is a question and then you have to get a bit practiced, to get a bit familiar. So today we are going to talk about pumping lemma for regular languages. After we finish this right quotient thing, some more regular properties, and then we will see when languages may not be regular, some properties, right? And you have to be a bit more familiar trying some examples and all. Yeah, I mean, if you have to solve some questions yourself, right? So this is not very difficult to understand, but it's important also to make yourself familiar, right? So that's why these exercises are not very difficult. For example, this thing, it's not very difficult, but you need to do it like so. I have shown two of the cases. So this one case you have to try yourself so that you become familiar with the way things are happening, right? Uh, yeah, I mean the thing is that otherwise, when there is a question that you see, if you are writing an exam or sometime even if some other time, like if you plan to take it for qualifier, it will be very difficult. I mean, unless you are doing these things yourself. So, right. Okay. So let's start with the closure properties under right quotient. So what is the right quotient? What did we say? So suppose L1 and L2 are two languages on the same alphabet. Then the right quotient of L1 with respect to L2. So we are denoting it in this way. So it's essentially a word X. So this is a word X such that there exists some Y, so that X concatenated with Y belongs to L1 for some Y in L2. So the word Y should belong to L2. Clear? So for some Y in L2, you have XY in L1. Okay. Now here is an example. So A and Bm, A greater than equal to 1, M greater than equal to 0, right? So there can be at least one A, and the number of B's should be 0 or more, and union BA. And L2, what is this? There should be one or more B's, right? And now how are you going to define L1, the right quotient of L1 with respect to L2? How are you going to define it? What is this for this case? It's already written, right? So it's all those words. So again, if I have to say these things in words in English, so these are all those words which have uh, which have a suffix in L2, and the concatenation with the suffix belongs to L1. Clear? So this is the right quotient of L1 with respect to L2. Clear enough? Now, what is this then? So let's see again. So here you have A and Bm, n greater than equal to 1, n greater than equal to 0, and Ba, and L2 is 1 or more B's. So now what is An Bm here? Is this correct? So let's see. So if we are saying that these are those x's, right? So those things such that if you add something from B, right? If you add something from B, and then this is going to be in so if you add something from L2, then this is going to be in L1, right? So for example, if you consider A3, right? If you consider A3, you can add some number of B's, and this is going to be in L1, right? So this A3 should be in the right quotient of L1 with respect to L2. And so if you see a bit carefully, you will see that this is the right quotient language. Clear enough? I mean, you cannot have this, or you cannot just have just a B, because you cannot append an A because A doesn't belong to L2. Correct? And you cannot also have BA because if you append something, some number of B's, BA, B, etc. So BA, B star, what you get, BA, B star, this does not belong to L1. Correct? So it doesn't appear in the right quotient. Clear enough? Okay. So the definition is clear, right? It's a set of all those strings such that you can append something from L2 to get a concatenated string which is in L1. Okay. Now the question is, we want to show that if L1 and L2 are regular, then the right quotient of L1 with respect to L2 is also regular. How are you going to do it? So suppose I make a DFA for L1. Okay, so there's a DFA for L1, DFA A accepting L1. And this is of the form Q sigma delta Q0F. Okay. Then what is the idea? Product DFA. So what is the product DFA? So product of what? Of which ones? L1 and L2. What is the idea? Yeah, sure. Very good. So you are talking about, like, suppose you have a path, right? So you have some Q0. So what are we talking about? Suppose it goes to some Q and then there is something like this. So you can have an X and you can have a Y. So let's again look at the definition, right? So let's look at the definition. So the definition is here, right? So I am first I have considered a DFA on having this thing, right? And you have XY, then what? Yes, very good, right? And if there is such a path, then what you do? So suppose there is a path. Suppose there is a string from from Q to some accepting state. So I should call it QF maybe. There is a string from Q to QF. String accepted along the path from Q to QF. QF that is in L2, right? Then what would you like to do? Make Q, then you would make Q accepting. Very good. Then make Q accepting. Correct? Then you would make Q accepting, right? And you would do this for every. Correct. And how would you do that? So how would you do this check? if there exists such a string, which from Q to QF for some state, if there exists such a string from Q to QF, which is also in L2, how do you do this check? So you construct a DFA for L2, right? So to do this check, construct a DFA for L2, and then what? Sorry? You'd run L2. I don't understand this thing. I mean, you can have several such paths, right? The queue can be here. So I have fixed my queue for now. And I'm going to do this for every queue, right? So I've fixed my queue, going to do this for every queue. And so, and there can be another maybe QF also here, right? So how are you going to do this? So, and you, so yeah. Huh? There can be infinitely many paths. That's true. There can be infinitely many paths. So what can you do? So you are right that you have come to Q. And what are you saying? That as long as starting from Q, right? As long as starting from Q, you are reaching QF, right? By reading some word in Y. I mean, there can be several such possibilities, but as long as there is some word Y, it's fine. As long as there is some word Y. So you start from Q, right? And then you are following a suffix of the word xy. So you have this x and then there's a y. You are following this suffix y such that this is in L1, and you have the automaton for L1. You have the full automaton for L1, but here you are starting from here, okay? And then you are checking if there is some y, like it can be if there is a y1 or there can be a y2, whatever it is. So there can be a y1 here, there can be a y2 here. As long as there exists one, it's fine. And you also said it correct that you also have a DFA for L2 conflict. So what do you do? Sure. So can you state it a bit clearly? What can you do? Okay, so let me tell you. So what you can do is now you can construct a DFA with Q as the initial state and QF as the final state and have everything here. Whatever was there. So now you construct. So suppose your L1 was like this, Q sigma delta Q0F, right? And now I am saying that you consider AQ1. What is AQ1? It's the same as Q sigma delta, but your initial state is Q1. If, right? So what will this automaton accept? This DFA accept? This DFA is going to accept all those strings, all those suffixes, which you can accept starting from Q, right? So you have only changed your initial state from Q0 to Q1. So this is my Q1 here, maybe I call it Q1. Sorry? Exactly. So now you have AQ1, and suppose the DFA, I call it for L2, I call it A2. And now you take the intersection, AQ1 intersection A2, and what do? Check, very good, check if non-empty, right? Right? If it is non-empty, then what would you do? make Q accepting. So then you are going to construct the automaton for the right quotient of L1 with respect to L2. And that is again nothing but Q sigma delta Q1 delta Q0, right? So this is the automaton, I would say AL1 slash L2, correct? It's the same, but now you have such Q1s, such set of Q1 such that AQ1, right? I mean, I can even write here Q1 such that AQ1 intersection A2 is non-empty. Clear? Is it okay? So now what is happening? You are starting with this initial state you are starting with the initial state Q0 for the right quotient, but you are ending here itself because there is a suffix which is going there and getting accepted. There can be infinitely many such paths, but all you can do, in order to get all such words starting from Q1, you just construct the DFA with this as the initial state and see what is the language being accepted and take the intersection with the DFA for L2, right? It's a nice construction, but not either very difficult. I mean, everything. So since we started with L1, which is regular, so this AQ1, so the language that you can get of all these suffixes starting from Q1, that is also going to be regular, right? Correct. And hence you can take, we know that you can take intersection and regular languages are closed under intersection. So what you get is like, what you get here is something like this. This is also regular and you have a DFA for this, correct? And then check if this is non-empty. Check if it is non-empty. If it is non-empty, make Q1 final. Okay, make Q1 final. Then make Q1 final in a L1 slash 8. Clear enough? Right? So, okay. And you need to do this for every Q1. So we need to repeat this process for every Q1 belonging to Q. And whatever is satisfying this property, make for those Q1, make them final. Clear? Good. Now, so let's consider the reversal of a language. What is the reversal of a language? So you have the reversal of a language LR denoted by reversal of a language L denoted by this L superscript R. You consider the words W in L and reverse the words. So we call it WR, right? Where WR is the word written in the reverse direction, right? So if you have, for example, AB, if W equal to AB, ABB, WR equal to BBA, correct? How do you show closure under reversal? The family of regular languages is closed under reversal. How do you show this? Exactly, right? So what do you get? So if you start from a DFA for L, you reverse the direction of the transitions. Right? So if you start from a DFA, are you going to get a DFA here? Yeah. But it may be possible, suppose what you are saying is that you are taking disjoint union. That is what you are saying. So suppose if you have final states like this, right? These were your final states. And then you were saying that make them initial now. Make them initial states, right? And then you are saying take union. Will that work? The thing is, what you are not considering is that there may be some kind of, what is separate DFA? For each final state, you are going to make a separate DFA. But how are you? Because there can be in the final states will be connected. Yeah. Okay. Okay. So you are going to take this and then you are going to say that I can consider the union. Sure. So this is one way. The other thing is that you can also add the epsilon transitions, right? So you are going to have, so if you do the reversal, you may have, for example, NFA, but you can have, let's say, you have NFA, like maybe you can say, like there can be several multiple NFA, and right, and so we are saying that each corresponding to one final state. So if this is DFA A, final state of A, right? And this becomes, right now, this final state is the initial, it's an initial state in AR, right? But if you have them, you can also, what you can do is, you can also have one state and then join this with epsilon transitions, and you can get an epsilon NFA. But also the other thing is, suppose even other than that, suppose you have, let's say your sigma is AB, and I'm considering the DFA A, right, which accepts L, right? DFA A which accepts L, such that L of A equal to L. Now we are trying to construct AR, right? And you are saying that, okay, when we have this, we are going to reverse this thing. Now suppose this was A and there was another thing which had B here. This is fine, correct? But now when you are reversing, you see that you get here A and B, but not necessarily this. I mean, it's not necessary that there will be an A transition here to reach, right? It may not be necessary. I mean, in the case of DFA, you can have, say, A, B. Outgoing transitions, you have to be like it's a full function, correct? You have to have transitions on every letter, correct? But it's not necessary that you have to reach here also by reading a B, correct? So when you are moving the arrow in the other direction, when you change this, correct? So you may not have always an outgoing transition on. So you may have incoming transitions. So for example, incoming transitions will always be, you will have like the full set of incoming transitions on all the letters, but the outgoing transitions may not be on all possible letters. So it will not give you a DFA. What you are going to get, an NFA. But we know how to transform this, at least for this part, easily. Like whenever some letter is missing, you can add that letter and go to a track state, right? It's a track state, correct? Clear? Okay, so we also learned that regular languages are closed under reversal. Okay, so now we are going to talk about when are languages not regular. Okay, when are languages not regular? Do there exist languages which are not regular? So far we have seen only regular languages, but are there languages? So what is a language? L is a subset of sigma star. Can there exist languages which are not regular, right? So we'll start with this ANBN. and will show that this is indeed not regular. Correct? So what is the intuition behind this? Like you have, suppose the number of A's here has to match with the number of B's. Now it can happen that you have to remember how many A's you saw. And the intuition is that in a regular language, if you have a DFA, right? You have a finite state automaton, it has only finitely many states. And you cannot remember arbitrary number of A's, how many A's you have seen, like whether it's 1, 2, 3, 4. For this, you need to have arbitrary amount of memory. So this is the intuition. Now, how are we going to prove our intuition? Maybe you have seen pumping lemma, but suppose let's say we start from very basic first principle. How can you show? Huh? Hmm. Sorry? Considers strings of the form a to the power I. Okay. So could you repeat? So you have, so you are saying, suppose there is a DFA. Suppose there is a, suppose, okay, so you are proving by contradiction, first of all, right? So you're talking about proof by contradiction. So you are saying, suppose L is regular, which means there is a DFA accepting L, correct? There is a DFA accepting L. Then what? If so, then suppose, okay, if there is a DFA, okay, DFA accepting L, suppose DFA A. Suppose A has K states. Then what? Okay, so you consider some A 2K plus 1. Okay, that's also okay. Okay, so you are saying that there exists some I and J and I not equal to J such that AI and AJ, by reading AI AJ, we reach the same state Q. Then what from Q0? Nice. Then okay, and then from Q read BI, and so what happens? And so since AI BI belongs to L, okay, read QA and reach some QF belongs to F, right? Okay, but since this is the case, right? Now this implies that AIBJ also belongs to L, right? Because sorry, AJBI, this that AJBI also belongs to L, okay, and a contradiction. Now it's important to note that you get this construction, you get this contradiction only because A is a DFA. You couldn't have argued this had A been an NFA. Could you? right? I mean, the thing is, what happens is if you read your AJ, hmm, okay, so let's think about this a bit. Yeah, yeah. Uh, the thing is that when you consider the NFA, so even if you say that if I have um, right, okay, so you can still have, like, let's say there can be a run in the NFA so that you reach the same state. That can happen. Same, but if you consider one, suppose run, there exists some run, uh, you can still say that I can reach there from the initial state to this queue. And then uh, if you read this particular QI, it should still go to that accepting state. So I'm saying that suppose you have a, okay, so suppose, let me think. So suppose you have an NFA and there can be several such possibilities, right? Now, so I have this I have AI, and even if I consider an NFA, uh, I still can have, even if I have an NFA, there should exist some J, right? Such that I can reach the same uh, state, right? Because the NFA also has finitely many states. So there should exist some run such that by reading both AI and AJ, you reach the same state, right? Because you have finitely many runs, there should exist some run such that on AI you reach here, on AJ also you reach here, and then the NFA should have an accepting run on reading BI. And if you follow that accepting run, then by reading BI after reading AJ also you go there. So essentially the same argument should work for both DFA and NFA. Okay, so I think it's not that important here. So even if you have A is an NFA, then also the argument works. Okay, just think about it and let me know if you find anything. But I think it seems like it should work because you talk about pigeon hole principle. So the NFA, suppose it is accepted by an NFA of k states. Then since you can have arbitrary number of A's, so I can have an AI and I can have AJ, right? Two different paths, right? Since there are finitely many states, so I can have I and J such that by reading AI and AJ, I would go to the reach the same state. Okay, and then I can read from here, I can read a BI and I reach a final state. So there exists an accepting run for AI BI, also exists an accepting run for AJ BI, correct? So this works for NFA also, even if you consider. Good. So uh, now this specific thing was very particular to a language. Okay, right. Now, maybe I can ask some related question, which is here, that if you consider subset operation on a regular language, so you are given a regular language, so is the subset of every subset of a regular language regular, right? For example, if you consider A star B star, which is regular, but A and BM Yeah, then everything would be regular, right? And similarly, superset of every regular language, you consider an arbitrary superset, it may not be of a regular language, may not be regular, right? Just to, okay. So now we are going to talk about something called a pumping lemma, which is a generic way to show that uh, indeed, if a language is not regular, how can you prove this, right? So here, for example, we gave some argument for this language ANBN, right? Here we gave this, but now we are going to talk about a generic tool to show whether a language is not regular, right? It's a generic tool to show that a language is not regular. So have you studied the pumping lemma for regular languages, right? Okay, so let's quickly go over this. So what does the pumping lemma say? Essentially, so I'm going to write it. So suppose let L be a regular set. Let L be a regular set. Okay. Then there exists an N, a constant N, right? Such that for all Z in L, there exists a decomposition of Z into UVW. So what does that mean? So there exists strings UVW such that Z equal to UVW. This is what, okay? Such that, and UV, the length of UV is less than equal to N, okay? And here, Z, okay, so for all Z, here I should say the length of Z is greater than equal to N, UV is less than equal to N, and length of V should be greater than equal to 1. It cannot be an empty string, okay? And for all I belonging to the set of naturals, right, we have, so when I say set of natural, it includes 0. Okay, we have, what do we have? U, Vi, W belongs to L. So what is Vi? So the V appears I times, right? The string V here, it appears V dot, it appears I times. So this is UVI, correct? Okay. Now I'm just going to, I think it's very important to write this also formally in the sense that like by writing all the quantifiers. And so essentially, I mean, the proof is very similar to what we discussed, what you said just a while ago. So you start from Q0, right? And suppose you consider, maybe you consider a DFA A for L, right? DFA A for L, suppose this has K states, or suppose this has N states, right? And now you consider a Z belonging to L such that Z equal to M greater than equal to N, correct? So if you start from Q0 and suppose your Z equal to A1, A2 up to AM, right? And here you see that N has to be greater than equal to 1, right? It just follows that N has to be greater than equal to 1 because V is greater than equal to 1, right? And so uv is of course less than equal to n, but n cannot be 0. N also has to be of length at least 1, right? Because v itself is of length at least 1, right? Okay. Yeah. So here we are saying Q0, A1, Q1 like this, and sometime you have AI minus AI. Suppose you read AI, and then you go to some QY, right? And maybe from here you read up to AI plus 1 to AJ minus 1. Okay, or maybe you read up to AJ here, correct? And then here you are reading AJ plus 1. And so these are all, this is a string. So this is like the string, I call it the V. And then here you go QJ plus 1, and you are reaching AM, reaching QM, like this. And suppose QM, since Z belongs to L, QM belongs to F, right? So now you see that if you consider such a DFA, then you can pump the string arbitrarily many times. So the string which is A1, AI, AJ plus 1, so I've removed the part between AI plus 1 and AJ to AM. This also belongs to L. And similarly, A1, AI, right? AI plus 1 to AJ. And if I repeat again, AI plus 1 to AJ, then AJ plus 1, AM, this also belongs to L, correct? So if I repeat this string once, this also, and if I repeat this arbitrarily many times, then that also belongs to L. So this is like my V. So this part is like my U, this part is like my V, and this part is my W, correct? And you see that whenever UV is less than equal to N, UV is less than equal to N, so you have such a thing, like for V greater than equal to 1, you can pump the V, correct? So UV has to be less than equal to N, where you are going to see some state is going to repeat and you can pump the V. Clear? Okay, so this is this. So now what we said, we are going to state this. So let's state this a bit more formally. Let L be a regular set. So let's take this and right. So right. So just note this part, that if L is a regular set, then this thing holds, correct? Then this thing holds. What is this again? That for the regular set L, there exists some constant N. There exists a constant N. So I can say there exists a constant N such that for all Z whose length is greater than equal to N and Z belongs to the language, there exists a decomposition of Z into UVW such that the length of UV is less than equal to 1, less than equal to N, and V is not empty set. Then you can pump the V arbitrarily many times, and the resultant word is still in the language. And when I'm saying this I, note that I can be, note that I can be 0 also, right? I belongs to N, right? So it's essentially I greater than equal to 0. You can have this. So it means that you have removed the V, then also it should belong to N. And it's also important to note this part, that there exists a decomposition of Z into UVW. Okay. So in order to show that something is regular, okay, so if I give you the Z, you have to choose. So if you are trying to prove that the language is regular, suppose if I give you any arbitrary Z, you have the power to choose the decomposition. There exists a decomposition such that V can be pumped. Clear? It is you who should choose the decomposition. Suppose I'm trying to prove that the language is not regular and I'm giving you any Z, any arbitrary Z. If the language, you are trying to show that the language is regular, then you can choose to decompose the Z into, there can be several possible decompositions of Z into UVW. As long as you can show me that there exists such a decomposition, such that you can pump the V arbitrarily many times, it is regular. Clear? So this is very important. Right. Question? Okay, so I think let me write down it a bit more formally. So L is regular implies there exists N such that for all Z belonging to L, Z greater than equal to N implies there exists UVW, right? So this is what I was saying. There exists UVW such that, again, Z equal to UVW, right? And V is not equal to epsilon. It's the same as saying that length of V is greater than or equal to 1, whatever, right? So this thing, this thing is the same as this, right? I mean, you could have also written this. You could have also written this here, this here, this here instead of this, but they are the same, okay? And what else? And UV less than equal to N, right? And for all I, U VI W belongs to L. Now let me close the brackets. So this is what we are saying. So for all Z, if the length of the Z is greater than equal to N, then there exists if the length of the Z, right? So this implication is saying if the length of Z is greater than equal to N, then there exists such a decomposition such that this is V is not empty, then and UV is less than equal to N, and you can pump it and it is in L. Clear? So if L is regular, then this is this. But the pumping lemma is used more in its contrapositive form. Why? To show that a language is not regular. Correct? So we would like to write the contrapositive form also, which is very important. Contrapositive form, right? So what will be the contrapositive? What will be the, so there will also be an implication, right? So what is the, so suppose if you have P implies Q, the contrapositive, how do you write it? Not Q implies not P, correct? So what is the not P here? What is the not P here? L is not regular. So we are going to write that then L is not regular. So this part is clear. What about this part? So can you try writing this part? For all N, there exists a Z belonging to L, then what? Okay, so let me tell you one thing. So here I think I'm going to not write all the details, but going to write it in the form which is going to be useful. But so here when I'm saying Z So let me write. So when I'm saying that something implies something, so suppose P implies Q. So this is same as not P or Q, right? And we are considering here the negation of the whole thing, right? So this is, if you consider now a negation of not P or Q, this is like P and not Q, correct? Right? So what we are going to do, we are going to put this form, right? So what we'll do is, again, we'll keep the Z greater than equal to N, right? So we are considering this part as P not Q, right? And then since it is, we said that we are taking the negation, right? Because it's a contrapositive, so it becomes the whole thing, the whole of this part we are considering. So this is the whole cube. We are considering the negation of this. So we have started like this, and then it's like this, and so it again becomes this. And now we have to consider the negation of this, correct? So this is this part. So we have to consider the negation of this. So now for all UV W, what? Now again, you see that we have several conjunctions here. A and B and C and D. So suppose we have like, okay, so how many conjunctions? 1, 2, 3, 4. Okay. So suppose I have this conjunction A and, maybe I should write. Suppose I have these conjunctions P and Q and R and S. Right? So if you take the negation, what you can get is not P or not Q or not R or not S. Right? So can you write it in this form? P and Q and R implies not S. Isn't it the same? Not A or, right? Not of this or this, right? So not P, not Q or not of S. They're the same, right? So I'm going to write it in this form. So then what do I do? So again, Z equal to UV W and V not equal to epsilon and UV less than equal to N implies there exists some I such that U V I W not in L. Clear? Okay. So what is it saying? So now let's take this. So it's very important. I mean, you have seen the pumping lemma. Of course, it's very important to understand the quantifications, like how the quantifications are changing, how they are alternating, right? Who can choose what? I mean, whenever there's a quantifier alternation, you can think of this as a game. For example, I am trying to prove that a language is not regular, right? I mean, so this is what, if such a condition holds, then the language is not regular. I'm suppose trying to prove that the language is not regular, and you are trying to prove that the language is regular. Then what are your choices? What are my choices? So this is very important to understand. Clear? So now let's try to write this down again. So let me copy this. Right? So I'm spending a bit more time, but I think it's very important to understand these details. Right? I mean, proving examples, I don't think that's going to be too difficult, but the implications here, I think it's sort of like, I think it's going to be like, once you try doing 1 or 2 examples, we are going to do that, you'll see that it's not that difficult. But anyway, so now if I have to write this in English, right? So I'm going to write the contrapositive thing in words. Just, I think it's sort of important. So if for all n, so again not, if for all n, right, there is a word, so this is this, now I say there is a word z belongs to L such that z, the length of z is greater than 1, then the next thing is for every possible decomposition of z into UVW such that phi not equal to epsilon and UV less than equal to n, if there exists. So why the if there exists? So this part is within this, right? If there exists an I such that, and then also to talk about this implication, like, so that's why I introduced the if here. So actually this implication is the if here, sorry, is the if here, but yeah, I mean, it's essentially this implication I'm talking about. So here, this, okay, and such that UVIW does not belong to L, then L is not regular, right? So if I am going to prove that the language is not regular, then I am going to choose these things. There exists this, if this is the case, okay? And I am going to choose the word, okay? Whereas if you are trying to prove that the language is regular, then you are going to choose everything which is the for all part, right? I mean, you are going to choose this thing for every possible decomposition. So this is what you are, so this, the universal quantifiers are something that you are going to give me, and I am going to choose the existential quantifiers. So I will choose a word set, I will choose the power I, the number of repetitions, how much I can pump. I'm going to show that indeed I win if the language is regular, right? So now, so is it clear? Any question? Any question? Clear? Right? So this should be, this quantifier structure should be very clear when we are talking about the pumping lemma. Now, there is a, okay, so let's look at first maybe some application of pumping lemma. So can you show this? So we are going to show using pumping lemma that some of the languages are not regular. So can you show, for example, the language with equal number of zeros and ones? This is not regular. So you can indeed consider a word 0k, 1k, right? It's not the same language as that 0 and 1n. So we saw something like a and bn, correct? But it's not exactly the same. But the same argument, like you can right? You can use this. You can use the same word and show that and pump, right? So my k is like my n. So this k is like my n. So this n which is appearing in the pumping lemma, right? And what does it say? There exists an n. So as long as you can find there exists, and to show regular, but for every n you can, so you can choose So you can choose any k, right? Whatever k you choose, for every n, whatever you are choosing, so you are blue, I am the magenta, right? So whatever you are choosing, I am going to prove that it is not regular. So you choose any arbitrary k, right? And then, so uv has to be less than equal to this k or n, correct? So, and v has to be something. So correct? So for every possible decomposition, you can choose again the decomposition. So whatever v, so v cannot be empty, but you can choose your v, whatever. And I am going to show that I can still pump it and show that. So you are going to say some 0r, whatever this r be, as long as it's not, r is not 0, right? And I can pump it. So I can pump it even once. So then what I get 0 k plus r 1k, which is not in the language. Hence I win. The language is not regular, right? Similarly, what about WWR? What are you, and your sigma is 80. What can you do? Yeah, it's just that you are right. It's just that I'm talking about A and B are the languages. So I can say my Z equal to hmm? So you are going to choose the Z, correct? Sorry, you are going to choose the K or the N. I am going to choose the Z, right? So you can choose some K, some K. I am going to choose this word. AK, BK, BK, AK, correct? So the V has to be only some A's here. So the V again is of the form some AR, correct? Clear? Because UV is less than equal to UV is less than equal to K, right? And now I can pump and it doesn't remain. It's clear, right? Good. What about this NAW, NBW? NAW less than NBW? You choose some K. I have to choose the Z. So I will choose, right? So what Z can I choose? A to the power K, BK plus 1. And you are done, right? I pump it a few times, correct? For every decomposition, right? I mean, even if, so A, even if my V is A, any decomposition you choose, even if your decomposition is just A, I am going to pump it and show that, even if it is just A, correct? This is possible. You can give me such a decomposition. I'll pump it at least once, and A and B's are equal. Even if I pump it once, I get AK plus 1, BK plus 1, and it's not in the language. Clear? What about this? NAW not equal to NBW? Sometimes it's not also, I mean, okay. So here maybe what I would say that there may be some applications of pumping lemma. But I would say for now, show that this language is not regular. I mean, can you use without using pumping lemma? Can you use in some other way? Some closure property. Very good. Not regular. So the point, what I'm trying to say is that whenever you see something, it's not necessary that you always have to apply pumping lemma, but or you can use a mix of pumping lemma and closure properties. So what can you do? Sure. So what closure properties do you know? Intersection is one. Other things? Sorry, complementation. Yeah. So can you use complementation? Right. So you can say if L is regular, then L bar is also regular. And what is L bar? NAW equal to NBW, right? And this we saw is it's exactly same as this, equal number of zeros and ones, right? It's not regular. Hence, L is not regular. So, right, we saw that not regular. Hence, L is not regular. Clear? Next, prime. So now you have to prove that you are the one. So I give you some AK, some arbitrary AK, where K is prime. How do you show that this is? You have to show that I give you some K. You have to choose. You have only one option. It's like only AK is what you can. I mean, you have actually more than one option. Sorry. So you can have anything greater than equal to K. You can choose some AK prime also, whatever. Right? But okay, just to AN, suppose you choose. Then so suppose your length of V is I. So V equal to AI. Then what can you do? N plus I. So you pump it once, you get N plus I. Pump it twice, N plus 2I. You are trying to prove that this is not regular. This language is not regular. So you have to find an I. Does there exist an I such that the resultant word is exactly? So N plus Ni, right? It is not prime. It is not regular, correct? Clear? Okay. Okay. Good. Okay. So this is N plus Ni is not prime, right? So sometimes, I mean, often you can prove things using pumping lemma, but sometimes using closure properties can make things much easier. Okay. You can also maybe try this directly with pumping lemma. I mean, it may be possible. I didn't try it, but using closure properties, it becomes much easier. Now, what did we see? Okay, so let me finish with one last thing. What did we see? We saw that if a language is regular, let L is let if L is regular, then it satisfies the pumping lemma. Then it satisfies the pumping lemma that for all words in this such that the length of the word is greater than equal to n, there exists a decomposition such that the part that you pump is not epsilon and uv is less than equal to n, and for all I, if you pump it so many times, it is in n. Clear? So all I'm asking, so this implication is that if L is regular, then this has to be satisfied. What about the converse? So what is the converse question? Converse question, converse of pumping lemma. It's not contrapositive, right? It's converse. right? So we ask this. If this is the case, does it imply that L is regular? So if a language satisfies, if a language is regular, it satisfies the pumping lemma. If a language satisfies the pumping lemma, is it regular? So the answer turns out to be no. Okay. So the answer turns out to be no, right? So let me write this. So what does it mean? There exist non-regular languages, which satisfy the pumping lemma. Clear? What are we saying? So we are talking about the converse of the pumping lemma. So what was pumping lemma? If a language is regular, then you can pump a V, which is not epsilon. Converse is that if you can pump a V, which is not epsilon, then is the language regular? And it turns out to be no, which means that there exist non-regular languages which also admit pumping. So I'll give you an example. I mean, it may not be very easy to come up with this. So consider this language, a dollar. So what is my sigma? So here the sigma is A, B, dollar. Dollar, A, N, B, N, N greater than equal to 1, union, dollar K, W, such that K is not equal to 1, W belongs to AB star. So let's look at this a bit carefully. Suppose I call this language L. So it starts with a single dollar, this part. So it is a union of two sub-languages. It's a union of two sub-languages. So the first part, it starts with a dollar, then it has A and B N. So of course the A and B N, even if it is N greater than equal to 1, we know that this is not regular, this part, right? This part, you can have 0 or 2 or more dollars, dollar K not equal to 1. You cannot have $1 in this part. $1 is possible only here. And then the W can be anything in A comma B star. So this is the whole language. This is the whole language. It consists of these two parts, L1 and L2. Right? Now, I want you to understand yourself. I mean, you should understand yourself that indeed L satisfies pumping lemma. L satisfies the pumping lemma. Right? So there should exist a decomposition. There should exist a decomposition, right? In order to satisfy the pumping lemma, you can choose the decomposition of your choice and you can pump the V arbitrarily many times. Clear? So I'm going very slow over it, repeating several times so that it becomes very clear, right? And so this is one thing. And then also prove with whatever you have learned so far, pumping lemma, closure properties, etc., that L is not regular. Clear? So I'm giving you this language L. So how can you show that L satisfies the pumping lemma? So what are you going to, what is your V? What is the pumping string? V is dollar. Okay. So if you, so of course, so you can choose your word such that you have a dollar is your V is dollar, right? So we are going to, so this part is regular, clear? This part is regular, clear? You can draw draw a DFA and FA for this. This part is not regular, correct? So in fact, for this part, you can easily show that this is going to be like, it will satisfy the pumping lemma for this part. So something if it doesn't, which is more interesting is this part. So what is your V? V is dollar, right? And you pump. So suppose you start with some dollar, suppose your Z, suppose is dollar A2 B2, you start with. You pump the dollar. You can either remove it. So what do you get? A2 B2. A2 B2 is here in the right part. You pump it more, correct? So dollar A2 B2 is also there here in the left part. You pump it more, you get some dollar K A2 B2. If K is 1, then it is belonging to the left part, right? If K is more than 1 or less than 1, then it is in the right part. So you can pump the dollar. It indeed satisfies the pumping lemma. You can show a decomposition and you can pump it. But now I also claim that the language is not regular, which is intuitively correct, right? Because this part you have, how are you going to remember that followed by the dollar, you have to, like if it is a single dollar, if your word starts with $1, then you have to remember the A's and the B's, the number of A's, they have to be equal, which you cannot do intuitively with finitely many states. But how are you going to prove this formally? Ah, let's say, okay, let's say you have a DFA for L. Yeah. So this is, suppose I call this L1 and I call this L2. So what you are saying is that if L is regular, then since L2 is regular, thus L, this thing is also regular. This is what you are saying. This is your argument. L minus L2 is also regular. So what you are saying is that then you get L1 is regular. So then you have to, so far you have to prove if L is regular. So what you show is that so far if L is regular, it implies L1 is regular, right? But suppose now you have to show that indeed L1 is not regular. How are you going to prove that L1 is not regular? Pumping lemma. L1 is $a and bn. So what will be the, how are you going to show this? Right, so you have to choose a V, right? So you can have $a and bn, and the V can be either dollar or $a or just A. Right. Yeah. Right. Correct. So you can show this, and then it is indeed not regular, and hence L is not regular. Right. Sorry. L minus L2. Yeah. 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 Correct. So L minus L2. This is same as L1. This is L1, right? L minus L2 is L1 because they are indeed disjoint. Correct? Because the number of dollars, it's not the same in the two parts. Right? And you can show this. Okay. Another way to do this using homomorphism, maybe. Right? What you can do, so I mean, you can also do this. For example, L, so let's say L intersection. Okay. This is just another way of showing this. So you already proved this. L intersection $A star B star. What do you get it? What do you get? L intersection $A star B star. Yeah, so this is L1, right? Because there is a single dollar only in L1, but single dollar doesn't exist. So L1. Now you have to, again, you have got L1 and you have to show that L1 is non-regular, right? So you can do a homomorphism. Suppose you have an H homomorphism. You can consider H dollar goes to H of dollar equal to epsilon, H of A equal to say 0, H of B equal to 1. Right? So my sigma is here dollar $AB and my gamma is 0, 1. Okay, so it's sigma star to gamma star is my H, my homomorphism. So now what is H of L? H of L1? Yeah, it's 0n, 1n, n greater than equal to 1. Correct? H of L1 is this. Now, what do we know? That if L1 is regular, then H of L1 is also regular. L1 is regular implies H of L1 is also regular. But this we have already shown that this is not regular. Hence, L1 is not regular. Hence, L is not regular. Right? I mean, here, if L intersection, if L1 is not, if L is regular, taking the intersection with another regular language will give you a regular language. But since L1 is not regular, what we have seen now, L is also not regular. Clear? So it's just another way of proving. I mean, you can prove, of course, in different ways, right? Okay. So we have seen this. So we are going to end now. So next lecture, we are going to see some more applications of homomorphism. And finally, yeah, I think then we'll start in the next lecture, Myhill-Nerode characterization. Clear? So let's